Good morning. It's my pleasure to be here. And again, I want to thank the Embassy for putting this on. We're here actually for a meeting from what's called the Group on Earth Observation. It's an international group of us that look at how we observe the planet. That's not only from space, but also from here on the ground. So all the technologies that we use to characterize our planet, that's what we're talking about this week. And so that's one of the reasons why I'm here as the director of the U.S. Geological Survey, is to represent the United States as the co-chair on this meeting this week. But wherever I go, I always like to come and visit with you guys, right? Visit with the future. You guys are the future for where we're going to go. So we're going to pass that from us old folks. We're going to hand it to you because the future's yours. So I want to give you a little perspective on the things that I did, which were a lot of fun. They were a lot of challenges. And then we're going to talk a little bit at the end about the challenges that you are going to face and where we're going. You're going to shape the future. I'm going to give you a few questions to consider when you get to that future on what you want it to look like. What do we have to know to do some of the things that you might want to do? So we're going to talk a little bit about that. But first, my background is geology geophysics. And I went into geology primarily because I loved it. I didn't go into geology because I could get a job at it. That's not what I was motivated by. I actually had taken an earth science course when I first went to university. I started out as an engineer in aerospace, thinking that was what was required to become an astronaut. I was wrong, obviously. I ended up taking a geology course, loved geology, and I transitioned into geosciences. And so that's where I got my bachelor's degree. I went to the Antarctic to do my master's degree, and I was looking at the rocks in West Antarctica, and they're the same age and the same composition, exactly the same type of rock as we have all the way up the west coast of South America, all the way up the west coast of North America, all the way into Alaska. The same granitic rock, the same age, which is Cretaceous to Jurassic in age, and the same subduction zone was the same process all the way along there. But that was my job to document that, and that's what I did in the Antarctic for 4 months. And I get a chance to go back, actually, in December. I'm going to go back for a really quick tour. I was there for 4 months in 1977. I'm going to go back for a week and go even farther in Antarctica than I did then, but we're going to do it really fast. So we're going to land in McMurdo, go straight to the pole, come straight back. We're going to go up the dry valleys, come straight back. Dry valleys are like Mars, by the way. And then we're going to walk over to Shackleton's hut, where all of his stuff from the 1910s is still there. And because it's so cold and dry, you could literally eat the crackers that are sitting there on the shelves if you wanted to, but you'll get in trouble if you do that, right? So I'm going to get a chance to do that. I did that also because I actually had a job offer, but when I got the offer to go to the Antarctic, I thought, well, I can take that time and go do it. So one of the key things I want you to sort of get out of my story a little bit is take advantage of things as they're presented to you. As things pop up, you have lots of time in your life. And so if you have an opportunity and you want to go to the Antarctic like I did, do it. When I went to work in the oil industry, I was working in what was then the frontiers, way out in what we were considered the deep water part of the Gulf of Mexico. And we were looking at these things called chemosynthetic organisms. And chemosynthesis is basically life processes without the benefit of sunlight. So no photosynthesis anywhere in the food chain. They live on chemicals. And in this case, they were living on sulfides and directly on the methane that were produced from the seeps that come naturally out of the floor of the Gulf of Mexico because we have a lot of oil and gas there. And those seeps come up and they provide a food source to these organisms, some of them quite complex and some of them quite large in terms of their colonies, that live entirely on that hydrocarbon food source. So key thing, life, it requires only two things. An energy source, not necessarily sunlight, that's the food, and then for us, water, because water is a solvent for carbon-based life. In space, you just have to touch things. Right? It's all about momentum. So if I want to move, I just grab the handrail and just barely pull on it, just a few ounces of force, right? And then I now move, and I just keep moving because nothing's going to stop me until I reach out and grab something. And if I want to adjust my position, I just touch things. And that's one of the cool things about being in space, is that it doesn't take any effort to do things. You can move very large, very heavy things. In fact, this part of the spacecraft right there, we actually trained to move that by hand. It's about, that was about 12,000 kilograms, but we could actually move that in space with our hands because there's no weight. We didn't have to worry about friction. We just put motion into it. You have to be careful about momentum, and we'll talk about that in a second. This is what it's like being out there on a spacewalk, and you can see the Earth in the background. This is one of the coolest views, really. One of the ones that I'll never forget is I was finishing up one of my spacewalks, and as I'm finishing up, I just stopped and I turned around and I looked, and we're over some territory. You know, I couldn't really tell what, except it looked kind of familiar. It was really red, right? It looked sort of like Mars. And I realized, that's Australia. There's all my friends from Australia down there. And so we were going overhead as I was finishing up the spacewalk and got a chance to see the center of the country. I'm going to go see that part of the country here next week in Alice Springs. Now there's what we did on our last mission. We put that piece of equipment on. That's our solar panels. That's what it looks like right there. It looks just like, and it's essentially the same technology as solar panels you use here on the ground. And it's all about just generating power from sunlight, because we don't have any other means of making power in space unless it's nuclear. And we don't really have that option with the space station, so we use that. So here's a view looking backwards. This is what the station looks like now. These are that's the Japanese laboratory, the European laboratory, the US laboratory right there. It's basically a big laboratory in space, and that's what we have in space. And this is what it looks like assembly complete. That's what we have right here. Now these are some of the things that life in space, if you want to eat in space, that's what it looks like. Actually pretty much the same thing you and I might eat here. Only a couple things that we don't have. Don't have a lot of fresh food because there's no refrigeration in space. So we don't really have a lot of things that require refrigeration. And we also don't have bread like you and I would eat here because crumbs are a problem. And so we have Mexican flatbread tortillas, which we eat in space. And we eat out of the little packets that you see right here. But it's pretty much the same stuff you and I would eat here. Cream spinach, spaghetti with meat sauce. One of my favorites was cream and mushroom soup. Chicken with rice, whatever you wanted. And you had to pick your meals, though, about 4 months in advance. And so so imagine this afternoon if you went and sat down and had a 28-page menu and you have to figure out every meal you're going to eat for 2 weeks in 4 months. That's what we had to do. So you better hope you like it, right? Or trade with somebody on the flight if you don't. Right? Some of the things we don't have to worry about is housing, right? But this is something we do have to worry about, and this is an issue if we go to space for long duration missions and we leave the Earth. You're seeing this is obviously the Aurora Borealis, and there's the Australis as well down here on this end. And that's the radiation coming off of the sun, the charged particles that are being trapped in the magnetic field lines of the Earth, and then it hits the upper atmosphere. The green and white glow you see there is the oxygen and nitrogen that's glowing because of the charged particles. We have to worry about that stuff. If we have a significant solar storm, then there's a possibility we have to leave the space station and come home. Once we leave the magnetic field of the Earth, now you're exposed to that interplanetary space. That's actually a big challenge to go to some place like Mars, and we'll talk about that here in a minute. But if we do want to go to Mars, one of the things you're going to have to do is recycle pretty much everything. You're going to have to generate your oxygen, recycle your water, do the things that we sort of talk about doing here. But we don't do a complete recycling here on the planet. But imagine if you had to recycle 97% of everything to do a Mars mission. And that's what we're talking about having to do. Imagine that. Already this morning, every single one of us have thrown away more consumables in the course of our day up to this point than you could throw away in 3 years on a Mars mission. And so we're going to have to get a whole lot better about how we manage our environment when we're in space, when we go to Mars. And so we're also going to have to recycle our atmosphere. So plants do that for us here on the planet. We're going to have to grow our own plants, and so we're going to recycle the CO2 through the plants. That'll give us the oxygen. We'll eat the plants, of course, that's part of our food supply. So now we're going to recycle water through the plants. We're going to recycle air through the plants. We're going to eat the plants. We're going to recycle our byproducts through the plants because that's a fertilizer source. So now you have to get this really totally enclosed system. And that's a big challenge because we don't really know how to do that very well yet. Coming home, this is what it's like to come home. So we were doing 25,000 kilometers an hour. We're going to turn all that speed into heat when we hit the upper atmosphere, and that's what you see here. That's actually the shuttle Atlantis right there on our last mission going through the atmosphere. This is what it looks like from the inside. This is a wind tunnel model. That temperature right there is it's about 1,000 degrees centigrade, a little over 1,000 degrees centigrade, hot enough to melt most steels. And so we have to be protected from that by the thermal protection system on the orbiter. This is what it looks like from the ground. The shuttle's inside that head of what looks like a meteor, and it's really impressive actually to see it from the ground. This is what it looks like inside. We're going to do our Deorbit Burn and watch the timer right there. We just fired our engines. Now we're going to slow down just enough to hit the upper atmosphere. This is what it looks like inside. You start seeing this glow come through the windows. That's the atmosphere glowing red, soon to be white hot. And here you see the crew on the flight deck, and over the back you'll see that in the background. And then when we hit the upper atmosphere at just the right conditions, we actually hit it going 25 times the speed of sound. It's called Mach 25. We actually get a little patch that says Mach 25. I don't have it on this jacket, but I have it on my flight suit. And then we start feeling a sense of gravity as we're starting to decelerate. And that's what you saw right there. We come overhead, we're still doing over Mach 1.5 when we come overhead at Kennedy Space Center. So we announce our arrival with 2 sonic booms, one off the nose and tail. And then we slow down, we continue decelerating, and now we start lining up just pretty much like a regular airplane at this point, except a whole lot steeper. So when you see the airliners landing out here at the airport, for example, you'll see them, they're about a 3-degree glide slope. We're doing about 18 degrees, so we're 6 times steeper coming down, and it's pretty much like coming down on a piano. And then you pull the nose up, and then you start to land more like a regular airplane. And so we actually aim for a spot in the swamp, but that's where we're going to land. And so now we pull the nose up, and we'll come across the edge of the runway at about 195 miles an hour, about 205 kilometers an hour, and then we're going to touch down just about the same speed as an A380 when it's touching down out here. And then we'll roll to a stop, and then when we roll to a stop, we've done 220 orbits and about 18 million miles total credit that I've got my credit on the mileage. And this is what it looks like. Now all 6 of us standing right here actually feel really disoriented right here because we've just come back from space. Remember that otolith thing? We're all feeling just a little bit iffy. In fact, we're not allowed to drive a car for 3 days because of those conditions that we have there. Atlantis is now on display. If you ever get a chance to go to Kennedy Space Center, stop by and take a look at my ride into space 2 times. It's really spectacular. This is how we're getting to space now. At this point, we're going up on the Soyuz. Notice it's not a very glamorous ride. It's a pretty rough one getting up there. It's with the Russian Space Agency, but they've been flying this thing since the 1960s, and so it's got a long history, very robust vehicle. But we're going to start flying this vehicle here. We're going to do some testing on it here in the next couple of years. This is called the SLS, and this will hopefully take us back to the moon and onto Mars. And this is what we're going to fly in the interim. These are our commercial spacecraft. One of them here is by Boeing. That's what you see here. And then SpaceX has theirs. And then we've got some Lockheed Martin components and others that are building commercial spacecraft. This will take people up to the station, low Earth orbit, and back. But Boeing, what do they build that you and I fly on all the time? Airliners. They're already thinking about what a space liner is going to look like. In fact, they call this, the CST-100, they call it their first space liner. And so they're already thinking about how are you and I going to fly as you get older. You almost certainly, within your lifetime, you'll buy a ticket, just like we buy tickets today to get on Qantas. You'll buy a ticket on Qantas Space Lines or Virgin Space Lines or whoever it is, and you'll fly from here to the US in 4 hours instead of 14. It's worth the ticket. Right, so we've already done a first test with the Orion spacecraft, which is a government vehicle that'll hopefully take us back to the moon. And we just launched an initiative in the U.S. to do that in 2024. That's a pretty aggressive schedule, which means we've got to get to work on that right now. And it's going to be not just a U.S. program. It'll obviously be, because of the success we had with the International Space Station, it'll be an international program. So the good news is the Australian Space Agency almost certainly will be involved in that. So if you have an idea that you'd like to go to space, you guys are going to have that opportunity here in Australia to talk to your folks here. But the nice thing about going to space is that pretty soon after we go, these guys will show up right after that, right? So we'll have commercial capability in space again. But that's really why we go to space in a lot of ways, is that we look for ways to expand markets, do things that we've never done before. That becomes commercial products that you and I use. In fact, almost every day, you and I use one of them, right? How many of you don't have one of these? Anybody not have one? There's 2 people. Yeah. You know, this is amazing, right? So everybody has one of these days, right? And now the camera that's in here, that camera, the technology that's used for this camera to work and give you the image that looks really good, it's actually one that we developed to work in space, and we used it on the external tank so that we could look at it from space. Very lightweight. Data compression requirements, but giving you a high definition image so that we could see things in space. That became the camera that came in here. The components in here, you have actually more computing power in this thing that's in your hand than they flew the missions to the moon with and back in the Apollo days. Right? So this is why we go to space. This develops the things that you and I use on a routine daily basis. Now let's say we want to go to Mars. How many of you guys would like to go to Mars? Outstanding. All right, now, how many of you guys would go to Mars knowing that you're going to be gone 3 years? That's a pretty good return. That's usually pretty good. Now, this was part of the movie The Martian, right? Now, everything about that movie The Martian was plausible with the exception of that windstorm at the beginning. That was nonsense because the atmosphere of Mars is essentially a vacuum to you and I. The wind speed has to get up to about 270 kilometers an hour before you'd actually get things lifting and where you'd actually be able to feel it. So that windstorm thing, not so much. And Andy Weir, who wrote it, said, yeah, I just had to have something to generate this scenario. But on the surface, now I've always loved this image right here. This is actually filmed out in North Africa. And this is Matt Damon. He's standing out here and looking across this surface that looks like Mars. But the interesting thing about it is that because of where Mars is, the sunlight, the strength of the sunlight is about half of what you and I see here. So it's about, if you were actually on Mars, this would be what it would look like at noon, right about here, what you guys are seeing in your seats. That's about what it would look like at noon. So now you have to think, that's energy, right? So we're going to have to figure out how we're going to build our energy. Now the other thing is they had those little solar panels that he's carting around. Those things are going to be huge because you're going to need a lot of it to get the same amount of power that we would need here. The other thing is that he was using all these mechanical and chemical systems to generate the atmosphere, to purify the water, do all that stuff. You can't do that. It's way too expensive and too massive. That's the expense, right? Now, expense is measured in dollars, but really when you go to space, it's measured in kilograms. And so I asked the question in a class I was teaching in university. I said, what would it take to actually build that mission? It turns out to be as much money as we spent on the Apollo missions, which would be about $100 billion US for one mission, that one. So Mark Watney can go grow potatoes on Mars. So we need to think about that differently. How are we going to do that? We're going to have to do that where you're literally taking a small ecosystem like we talked about, where you're recycling everything. You're going to take a mini Earth, design it to go in a spacecraft, and that's what you're going to fly to Mars. How good are we at doing that today? Do you think we could build a mini Earth? Yeah, actually not even close. Right? We really don't know what all those variables are, but we need to because that's our ecosystem. We really need to get to understand this place a lot better than we do today. Now, one of the benefits is we do that to take ourselves to Mars. Well, that gives us that understanding so we can know how to live here a lot better. We only know about 1,000 variables, or roughly, right now on what drives our ecosystem. And that's probably not even close by 3 or 4 orders of magnitude. So we've got a lot of work left to do on that. So to go to Mars, we're going to have to build this system here and be able to do a robotic and human-tended system to go to Mars. Now, why would you go to Mars? Find out what the heck's going on. What's that? Mad flex? Yeah? Well, you'd certainly have that. What do you think? What? Yeah? So what would you want to know about Mars? What do you think you'd find out there that you might find useful or interesting? Why would you go? Why would you spend all that money to go to Mars? Map its geography. Actually, we can do that from space quite well. But why would you put the human there? Yeah, there might be things that, commercial things that we might find useful. Manage overpopulation. Yeah, we can send people we don't like to Mars. I like that idea. Right? What do you think? We get to see something different, right? That's probably the most important thing when we go to Mars, in that we see something different than this place, right? Because we've seen something different, we now start asking the questions about this place differently, don't we? And so there's actually 2 things about Mars that are sort of unique and unusual. It's a CO2 atmosphere and it's very low pressure. But there's something neat about it in that we're finding methane in the atmosphere. And that methane goes up and down with the seasons. And it does exactly that same thing here on Earth. Where does that methane come from? And it's seasonally driven. For what? Carbon life, yeah. So we're seeing methane as a byproduct of life here on the planet, and it goes up and down with the seasons, because as things expand in the summer and then it decreases in the winter, Well, as it decays going into the winter, you see increased methane coming off for that period, and then it drops off in the winter. And then when it comes back in the summer, it increases again. And so we see that cyclicity in Mars. But where would that be? There's no plants. Ice in the poles. We actually have ice elsewhere, too. That's a good point, though. What do you think? Say again? Living under the Earth. And actually, that's a good point. There's actually two things about that. One is there's no magnetic field. Like you saw that aurora earlier, there's no magnetic field on Mars. And so there's no auroras on Mars. That radiation hits the surface of the planet. So nothing's going to live on the surface, but right underneath it is the ice. And remember what we had to have for life? Water and something to eat, right? We've got methane. Methane we know works on chemosynthetics. So ET might be bacteria, and it might already be on Mars. Now, the question that I asked earlier about why would we send humans is that you are the best exploration tool we've got. And why is that? Because you do something called adaptive reasoning. You don't even know you're doing it. Everyone does it. We do it all the time. You look at something, you don't necessarily know what it is, but instantly you start thinking about what could it be. And so you have that ability to learn on the fly, which machines don't do very well. We have a way of processing logic differently than we can program into machines. And that's why the human, even though we're very expensive to move around, you're still our best exploration tool. Until we can get a machine that does what you and I do naturally, you are still the best way to look at something we don't expect. If you get to Mars and you see something there that you've never seen before, there's a possibility that that machine would never be able to figure it out, but I almost guarantee you'll probably get close to it because you'll be looking at it making free associations until it starts to make sense, and then you're testing the hypothesis, literally going through the scientific method until you come up with an answer. And that's why we send you to Mars. Right? But the fact that we would go there, remember, we'll have to understand the ecosystem here a lot better. We're going to build a mini Earth to get there. We're going to have to recycle everything. All of that knowledge comes back here where you and I can use it every day. You know, if that's something that we can use, that's the biggest reason we go to space, is figure out how we can do things better here on the planet. So here's a little human enterprise at the end. This is what it's like to actually design for a spacecraft. You also have to design for the things we do well, but also those things we don't do so well, like forgetting your keys. Right? So when you're designing a spacecraft, the last thing you want to have to do is go looking for your keys and realize you left them inside when you're 240,000 miles away. So I want to thank you for the opportunity to come chat with you a little bit today. We focused a little bit on space, but also we tied in some of the things that we do in the USGS, US Geological Survey. And then we look at hazards in our natural realm. We look at the ecosystems that we've talked about. We look at water, which is one of our biggest resources and also one of the biggest challenges that we have on the planet, fresh water for all of us. And here in Australia, you guys have had those challenges recently, but we have the same ones in the US and the West particularly. And then energy and mineral resources. So we have all those things that we work on in the US Geological Survey. We're working with Geosciences Australia, and I was visiting with them yesterday. And so we've got collaboration that we're already doing, and we're going to expand that even more. And then the other thing that I'm looking forward to, a good friend of mine, Pam Melroy, is working with the Australian Space Agency. And so the space program here in Australia is something that we're going to be working with you even more. Now, we have been working collaboratively with Australia and the US on a program that USGS operates, and that's the Landsat spacecraft. We've been doing that for over 40 years. And you guys know the history out of Tidbinbilla, right? So out of Tid, that's where the first video came down from the moon of Neil stepping out on the surface. So about not quite a second before everyone else, you guys saw it first here in Australia. So you have a first in seeing Neil actually uttering those immortal words there on the surface of the moon, even before we saw it back in the States. So it was my pleasure here to chat with you today. And I think we have time for a few questions.